the dissociation of S3 from the aldehyde of sulfonamide type of compound. So this system shows that there is a covalent group interaction in the HBMC. And HEC, this functional group of EC also occurred, but not so strong that compared to the first pause. And the second one, the HBC of combination, the hydroxyl and hydroxypropyl make the channel hole structure. So when the weakest the TFSI from the polymer make mobility of TFSI is not good for the ion Le plus mobile mobility. So this make easier to pairing between TFSI and Li here. So this quite understandable. That's why the conductivity of the HBC is lower than two others polymer. So the conclusion of this work that complex hydroxy group of HBMC contribute to the increased number of smoking ion. And the molecular grouping simulation is good to know the chemical interaction between the XSI and the molecular system. So I think this quite interesting. I first just understand what importance of the docking molecule of our experiment. And the second one, this next generation of solid state will combine between the inorganic and organic compound. I use silica from non-derivative compound. And the silica we use to identify first kinetic, and the second one the modify of the silica. And from the plated image, we see that quite different morphological structure between the silica native and silica modified silica. And in the modified silica, this little bit this in native silica is like a regular oxygen nanoparticle, but in nanosilica, modified nanosilica, it's some maybe interface with protonization of the silicon occur, or this introduction because XPS3 cell, there's addition of the sulfur occur. Maybe there's sulfonic group attached with the surface. Theoretically, the strong interaction between the lithium and the donor electron is too strong. It's not good because the mobility of the ion is not faster compared to just on the coordinate. And from I already present in the previous slide that two possible mobility of the lithium ion in the solid state. First, in the segmental motion, like dynamic molecular interaction, usually occur in the amorphous structure. And the second one, ion hopping, usually occur in inorganic because there's defect usually. And the mass diffusion, like this liquid electrolyte. So in our case, if we combine inorganic and organic, so what happens and how actually how the interaction with FSI in the organic and inorganic compound. This next so we compare the experimental result using modified silica. This stripping grading in symmetrical cell is more longer stable compared to without modification of silica. And in the end of this not subscript different with this in HVASE there's potential drop with from 260 to 25 million volt. It means that the distribution of lithium as will form it, the shape is square shape. This means the distribution of the lithium on the surface or the lithium metal is quite uniform compared to some shape of the figure. So this the big question of our next study. Yeah, what the next stage? Is our group. This the promising study in the near future that interaction mechanism of lithium ion in organic and polymer system, and how about the role polymer functional group, because many kind of polymer. So which one the promising functional group can make SI dissociation and lithium ion move fast in the solid state in the ion mobility. And this third one, the transport mechanism of the lithium ion in the mixed structure in organic and inorganic compound. I think the short presentation, I think I hope is good for of the audience. Thank you very much.
Thank you very much. Those are all the very basic parts. So any question about it? Sorry, I got it.
Yeah, so thank you so much for such a wonderful presentation. So I have a question about the TFSI anion. I saw you were doing the molecular docking of the anion with the polymer pack. So have you ever done the molecular dynamic simulation of that system?
Dynamic.
Yes.
Yeah. I think the most dynamic that I was not looking at.
Yeah.
Yes.
Have you done like?
I relate with Indonesian guys. Yeah, maybe little bit the technical I don't understand maybe, but yeah, actually we use 15 molecular conformation to consider of this to present this kind of conformation.
Yeah, just I think I might have one comment. Maybe
Oh, yes.
it's gonna be like
Yeah.
maybe it can be useful for your future work. TFSI anion is really flexible, so they can rotate, they can bend like really easy. So when it's in like semi-solid or in polymer electrolytes, it can bend itself. So maybe like the docking itself cannot make you see full picture of it because they're dynamically bending and rotating between the transformer like constantly rapidly. So if you can do the dynamic simulation, it would help you see like the full picture of how they dynamically switch between like the ion transportation.
Yeah.
Theory.
Yeah. Thank you very much. Yeah. Actually, I am finding who a person or audience interesting about the case to just for case to simulate what happened actually in our system, how the molecular system interaction between anion and the big molecular macromolecular. Yeah, thank you very much for your presentation.
Thank you so much.
Okay, so any more questions?
So how do you ensure that this is motion itself? What before it not say apply? You can say direct this is motion. This is the charge of zero. Charge of motion.
So it's when you first slide, you mean?
Why you can say? What is the reason why you can simply just say this thing is motion inside CM2 to bring up the charge? Why this thing is in charge of the charge transportation?
Just we this represent with the conductivity of the materials and just transfer this one this big equation actually in the looking molecular system with the dynamic of the MSRC, I mean the how to coordinate with the molecular system. And the lithium ion can when they trap on the polymer system, the lithium can move fast. So dissociation of the SI, Li and MSI is very important for the case for the solid state battery. So how strong the interaction anion with the that's for big equation. Thank you.
I think, we check on time, I think so. Thank you very much, Professor, for the next topic. And then we proceed for the last of today.
I think we are ready. Yes, should be good. So there was during the last talk, there was a internet disconnection. So that's why we had to restart again the system. So I'm sorry that I do not want to stop you. So maybe the audience on Zoom may lost a little bit of your talk at the end. Okay, so now welcome everyone back to our last talk, which will be given by Dr. Oxtier Fowley. So,
So
Dr.
the
Oxtier, could
yeah.
you start? Yes.
Okay, thank you. So the what you see in the Zoom is correct?
Yes.
Okay. Good afternoon, everyone. My name is Oktia, and I'll be presenting the computational study. Uh, I've uh, I've co-authored titled Interface Analysis of Lithium Chloride as a protective layer of LATP solid electrolyte for electrochemically stabilized or solid state lithium metal batteries. But before that, let me briefly introduce myself and my research topic. Yeah, my name is Oktia. I'm currently working in the Research Center for Electronics, National Research and Innovation Agency of Indonesia. My research interest is energy storage material, um, covering batteries, and then supercapacitors, and also battery recycling. But I have more interest in battery recycling, so I will uh, introduce you to some of our works. So basically, we do regeneration of battery from spent battery using hydrometallurgical uh, technique, using organic acid. The first paper we use for the first work, we use ascorbic acid, and then the second work we use malic acid. But the product, the final product is the battery itself. So we regenerate the cathode from the spent battery. And then actually I have never thought about doing computational work before, but because I'm joining this conference, so I try to search for potential MD topics in battery recycling. So there's not much I can find about the molecular dynamic topics for battery recycling, but what I can find is the first one. Somebody tried to investigate the interaction mechanism of leaching solution and spent cathode powder. So they try to optimize the condition through molecular dynamics, and then try to prove it using experimental work. And then the second one is the recovery of lithium ion from wastewater, which they use MOF, uh, using ZIF-8 coated cation exchange membrane. So they try to make modeling using molecular dynamics, and also try to try to prove it using experimental procedure. So this also because of the, how can I say, small research, not small, very few research using molecular dynamics for battery recycling. This may become a change also for me to improve my work using molecular dynamics, but it's very maybe far from now. Okay. I will get back to the work I'm going to present. This work was published in 2023. The focus of our investigation is on using density functional theory, or DFT, to evaluate how a lithium chloride layer can serve as an effective barrier to stabilize the electrolyte anode interface in solid state batteries. But as a disclaimer, I'm not familiar with computational studies, so please bear with my lack of knowledge. To begin, let's first understand the motivation behind the study. All solid-state batteries are seen as a next generation energy storage due to their enhanced safety, mechanical robustness, and potential for high energy density. One major advantage of all solid-state battery is their ability to use lithium metal as the anode, which has a theoretical capacity around 3,000 milliampere hour per gram, much higher than graphite anodes. And LATP has emerged as a promising solid electrolyte because of its high ionic conductivity and good chemical stability. However, there is challenge for this material to be applied, particularly at the interface between the LATP and the lithium metal anode. There is a formation of interfacial resistance between the lithium metal and the LATP. Okay. That's the end. Okay, let's skip this. And then, so the problem is when LATP is brought into direct contact with lithium metal, for zinc oxide, aluminum oxide, even boron nitride. However, these materials often require complex processing or may not offer the optimal combination. So what we need is the material that can effectively block electrons while still allowing lithium ions to pass through freely. And ideally something that's simple and cost effective to apply. So why lithium chloride? First, lithium chloride is known as a wide band gap material, making it is a strong electronic insulator. This means it can effectively prevent the flow of electrons from lithium metal to LATP. The second is it has good lithium ion conductivity properties, especially when used at grain boundaries or at as interfacial modifier. And then, okay, it also has a wide electrochemical stability. So the hypothesis we test in this study is whether a thin layer of lithium chloride can serve as an effective barrier to electron migration while allowing lithium ions to transport efficiently. So the computational method we are using is first, we're setting up the interface heterostructure using VESTA, and then optimizing heterostructure, and then the FT calculation using FAST, and then partial density of state analysis of lithium, lithium chloride, and LHCP. And then also we do analysis on the interface model. And last is evaluation of stability and electronic properties. Okay. Here we look at the partial density of states for the bulk material, lithium metal, lithium chloride, and LHCP. As expected, lithium metal shows no band gap, confirming its metallic nature. And then LATP exhibits a moderate band gap of around 2.3 electron volt. And lithium chloride clearly shows a wide band gap about 6.25 electron volt, confirming its insulating behavior. when we align the vacuum levels of these materials, we can predict the direction of electron flow. Lithium's Fermi level lies above the conduction band minimum of LHCP, suggesting that without a barrier, electrons will flow naturally and migrate to LHCP. However, lithium chloride conduction band lies about that of LHCP, making it an effective blocking layer for electron migration. So we compare to orientation, HA and HB. The HA structures show significant distortion at the lithium surface, while HB remains stable, consistent with its lower formation energy. The partial density of state reveal that the first two layers reflect bulk lithium metal, while the third layer, where lithium contact with lithium chloride, shows hybridization. The fourth and the fifth layer, representing lithium chloride, begin to show insulating behavior, especially in HB. HB also show cleaner band gap than HA. So from this, we can calculate at least the minimum thickness we need to provide in order to maintain the insulation. And then the second part is the HC and HD, which is the interface of lithium chloride and LHCb. As shown in the slide, both structure underwent structural changes after relaxation. And in HD, the interface arranged more significantly. The partial density of state plots revealed that the first and the second layers representing bulk lithium chloride, the fourth and the fifth layer representing the LHCp, while the third layer shows the hybridization. Okay, the HD shows a trap state at the second and the third layer. Possible, this make currently possible. And so that's why in this configuration, maybe thicker lithium chloride is needed. And this one is the charge density and stability. To further validate the electron blocking ability of lithium chloride, we introduce excess negative charge into the heterostructure and observe the resulting charge distribution. As shown here, the charge density difference analysis reveals that the excess electron accumulate at lithium and lithium chloride interface, but they do not penetrate further into the lithium chloride layer. And then we also calculated the partial density of state for the charge system and found that lithium chloride layers still maintain their insulating properties with large band gap reserve in the fourth and fifth layer. So this confirms that under non-ideal condition, lithium chloride can still effectively prevent unwanted electron transfer. And then we further examine the redox stability of titanium in the LATP when protected by lithium chloride using better charge analysis. This method allows us to detect changes in the oxidation state of specific atoms, in this case, titanium. So we found no significant change in the better charge of titanium. The value remain between minus 1.96 and minus 2.04. So there is no changes even if it charged. This result is significant because lithium chloride is indeed capable of protecting LATP. So to conclude, our DFT study confirms that lithium chloride acts as an effective insulating barrier for LATP, blocking electron migration from the lithium anode. These results suggest that lithium chloride may be promising as a protective layer, not just for LATP, but also for other solid state battery system. Okay, I think that's from me. Thank you very much.
So thank you very much, Dr. Okchia, for a very nice talk. And I think now is we can have a few questions from the audience. So some questions. Okay, good.
Hello again. Thank you so much for such a really wonderful talk. I'm really interested in the lithium ion batteries, like personally. So this is like really interesting presentation for me, as well as the previous presentation as well. So I have a small question about applying the additional charge inside the cell, right? How do you do that?
Actually, that's a difficult question for me because I'm not taking part directly on the computational work. So I initiated the idea. How about using lithium chloride as a protective layer? But my other college who did the calculation. So I'm not really, I cannot answer your question, sorry. Maybe I will share the paper if you need that, maybe can help you. I'm sorry.
I see. Thank you so much.
No.
That's fine.
Thank you very much.
Okay, so any more questions? I think maybe everybody getting tired. It's the end of the talk, and yeah, now I would like to ask everybody to give a big thanks to Dr. Accelerator. And now we will come to the closing sections, which I would like to ask Dr. Watanabe to give a little bit of talk about our nice workshop today. We can wait a little bit.
Okay, so then I'd like to thank you for all of your attendances to here. So then I personally think that we could have the good discussions, even though the meeting is just like a medium size or small size. I personally think, definitely I believe the discussions are quite good. Then we could exchange more things. However, maybe you could have more questions to the some people. So then tomorrow, I brought one room to discuss each other. Then if you are interested in, especially I asked to these people, definitely come to the CME again to discuss with us, but only before lunch. So then they have the plan to go somewhere. So then if you are interested in the discussions, and also if you want to talk with them and each other, the band is coming again in the morning 8:30 from the hotel and to bring to here. So could you please join? So as much as possible. So only small room, but we can sit down together and talk each other as you like. いいですかね。すみません、よろしく。So then hopefully this is not only the one chance to meet together and to discuss how we can extend this discussion is the next question for me. So I will discuss I will talk with my colleagues how
we can organize this kind of wonderful opportunities for all of us again. Maybe not in Japan, but also maybe in Malaysia, Thailand, or Indonesia somewhere. So at that time, I will again circulate the notice to all of you. So could you please think about your attendance again to discuss your progress and techniques and your future, then gather again, work together. Only one people doesn't work for any research these days. We have to make a team, then work together, that have communications, then push up our researches. So let's try to that. So that is today's main purpose. So thank you so much for coming to be here, and also then they talk to each other. Thank you so much, all of you. Thank you.
Okay, so we also would like to thank Dr. Watanabe that make this happen. So bring us together, and now I think we really go to the end of the workshop, and I think that we would like to ask you to help us to evaluate or make a comment on the workshop today. So could you please share the QR code for? Yeah, we will have QR code to have the evaluation form. In order to have this workshop, we have to make report for the funding that we get to to have this. They will share the QR code, and then I would ask everybody, please scan the QR code and help us to evaluate the organization of the workshop today. Okay, please wait a little bit, so they could not find the QR code. Oh, we can do that. Okay, so they cannot share it now. So there will be the email that will send the QR code to everyone who register for this workshop. And please help us to evaluate the workshop. Then maybe in the future we can make it better, even better. And I'm very sorry for some inconvenient event happen for the internet connections or the missings of the sounds or the screen sharing. So, and thank you everyone to be here for today. Thank you very much.